Well, greetings, mathletes, and welcome back. Today we're going to be talking about polynomials, and we're going to go through a few things. The first parts of it, we're basically going to be introducing polynomials and some vocabulary, some terminology or nomenclature, jargon, in case you want any other synonyms for vocabulary. And then we're going to be taking a look at something called the function notation. And that notation isn't restricted to polynomials, but this is a good place to introduce it and get some practice using it. So it is quite useful later on. And then we'll actually be talking a little bit towards the end about how to graph equations that you don't know anything about their shape. How do you get a hold of what they are and learn something about them so that you can graph them in the future? So that's what we're going to be talking about today. And so let's go ahead and get started here. So first off, we want to talk about polynomials. And let's drop this line thickness down a little bit. There we go. Okay, so polynomials. Now, I find it easiest to start this way. The first thing I want to look at is a monomial. And if you look at the word monomial, you see the word mono in there, and that means one. And so that's a big indicator of what we're looking at. What a monomial is any expression that is made up of numbers or variables or both that's joined by multiplication, right? And multiplication only. I know there's an exponent in there, but that exponent means x times x, so it's still multiplication. A monomial could also be a number by itself, like -5. It could be a variable by itself, like a, right? But it's something that's joined all with multiplication. If there's more than one thing in there, it has to be stuck together with multiplication. And honestly, even a variable by itself could be written at like this a could be written as 1 times a. And so it's still a number and a variable being multiplied. But in any case, that's what a monomial is. And mostly what we have to do is be able to identify them when we see them. Now, the next one up is a binomial. And bi means two. Bicycle means 2 wheels. Biannual means twice a year. Or every 2 years. Excuse me. That's semi-annual. Is twice a year. But yeah, it's one of those things. Bi means 2, and so what it means is you have 2 monomials added together. So you could have something like 5 plus x squared. 3x squared plus 4x, 3xy plus 4xy to the fourth, right? All of those things are binomials. And it could be subtraction in there too, right? You could just as easily have, something like p minus 2. That's also a binomial. What makes a binomial is that you have 2 terms. And a term is anything that's separated by an addition or a subtraction, right? So monomials are 1 term. Binomials are 2 terms. And I know you guys are going to be shocked by this one. Trinomials are 3 terms. And actually, we're going to be dealing with these 3 the most. And so these are the 3 names that pop up the most commonly: monomial, binomial, and trinomial. So trinomials may look like this, right? It has 3 pieces to it. And that's what identifies a trinomial. Right? There's another trinomial. 5 plus x plus y is a trinomial. It's just anything that has 3 monomials added together is a trinomial. And again, what you have to be able to do is use this vocabulary. I'm not real big on testing on vocabulary directly. My philosophy on the whole thing is that if you're going to understand what's being asked of you, you should know what these words mean. And so basically, you have to know one when you see one. Now, let me get some of these examples off here. All of these, everything you see, monomial, binomial, trinomial, these are all in a class of functions called polynomials. Polynomial is the general term for these guys. And you know, there's more names than this too. If I had four terms, some people actually go as far as saying that's a quadrinomial. And that's fine. That's not something we're going to be covering this semester particularly, and I usually doesn't come up very much, so I don't focus on the vocabulary. Um, I'm actually curious. I've never done the research on it for a five term. What the correct word for it is, whether it's quintinomial or whether it's pentanomial. I suppose it just depends on whether it's a Greek or a Latin base. But in any case, um, yeah, there are names for other things, but these are the main ones. Okay, so let's go ahead and clear this off. All right. Okay, now the degree of a polynomial. Right, the degree of a polynomial has to do with its exponents. Um, if there's only one variable involved, it's actually really straightforward. So if I have something like, if I only have, let's look at one variable first. If I have something like this, right? The way I come up with the degree is I look at each term and what's the highest exponent over all the terms? And the highest exponent is a 3, so the degree here is 3. If there was a, x to the 7th plus, in fact, let's make it 4x to the 7th plus 8x squared minus 2x to the 5th, right? All I'm going to do is look for the biggest exponent, which is 7, so the degree here is 7. And it's the biggest exponent on a variable. Okay, so that's what it looks like with one variable. You just find the term that has the biggest exponent, and it's that biggest exponent. That's it. Again, this is more about being able to talk about these things, because there's different types of solutions when you have a second degree or a third degree polynomial, and things like that. And so we just have to be able to talk about these things, and you have to know what I'm talking about when I say them. Okay, so so that's what happens when it's one variable. It's a little bit different when it's two variables, but it's still not too bad. It's not a lot of computation. It's still one of those things you can look at, and if you know what you're looking at, then you're okay. So, yeah, let's just look at something like this. 2x to the 5th y squared plus 3x to the 3rd y to the 7th plus 4x to the 5th y to the 5th z squared. Whew, that's a lot of stuff there. So here's what you do. When you're talking, again, you look at each term individually, right? But when you're looking at the degree of each term, what you do is you add up the exponents, right? Because you have two different variables. I have an x and a y, but there's 5 x's and 2 y's. So really what you're kind of doing is saying how many times the variable shows up in that term. And in this case, it shows up 7 times. Over here, let's see, if I add this up, it shows up 10 times. And if I add these up, I have variables that show up 12 times. The degree of the polynomial is the biggest one of these. So that's a 12. This is a degree 12 polynomial. So you look at each monomial separately, figure out what the degree of each monomial is, and then take the biggest one, right? That's what you're looking at. And then the only other thing, if you have 0 variables, right, you have no variables at all, So you have like a 5. I don't know. I keep using fives. It doesn't really matter what number I pick, but if the monomial I'm looking at is just a number, the degree is 0, right? Just so we're clear on that, because technically there's a little x to the 0 hanging out, and if you remember the last lecture, x to the 0 is equal to 1, right? So it doesn't change anything. Okay, so that's how you figure out a degree. And again, degrees aren't too bad. It's one of those things, yeah, you just look at it and figure out which monomial has the highest degree, and then that's the degree of the whole polynomial. Okay, so let's go ahead and clear this one off, and we'll take a look at the next part here. Okay, so I want to talk about the function notation now. This is something that may or may not be new to you guys. In the past, when we've had things to evaluate, you get something like y is equal to x squared minus 3x plus 2, right? So let's say we had something like this. That 2 looks too big. There we go. Okay. And you were told, well, to evaluate when x is equal to, I don't know, something like -2, right? So if I'm looking at something like that and I want to evaluate it, what I do is I treat every x like an open slot. And then whatever x is supposed to be equal to, I just plug it in, right? And then I follow the order of operations after that. And if I'm following the order of operations, everything takes care of itself from here. So I can go ahead, let's see, -3 times minus, let's see here, we'll have to do the exponents first. So -2 times -2 squared is -2 times itself, which is +4. And then -3 times -2 gives me a +6 plus 2. And so I end up with 12. And so I know when x is -2, y is 12. Well, there's a little bit more convenient notation than this, and it's the function notation. And so this is how the function notation works. Let me go ahead and get rid of some of this stuff so we can compare these directly. So we already know the answer is 12, right? Now, this is how it's written in function notation if we want to find what y is equal to when x is equal to -2. I think of it as a function, and this is how it's written. I would write, for instead of y equals x squared minus 3x plus 2, it's f of x equals x squared minus 3x plus 2, right? So you would be given this, and you would be asked to find f of -2. Now, this is a convenient notation just because now what we've done is we've given this expression a name. We've called it f, and x is the variable that you're plugging into for this function f. So f is just a name. I know this looks like multiplication. This looks like f times x. It is not. It is a function named f, and x is the variable, is what it's telling you. If I want to find f of -2, what it's telling me is everywhere I see an x in this expression, I'm going to replace it with a -2, just like we did in the last place. So it's just telling you what to plug in for x is what it's actually doing. So we just plug our -2 in there, -2 in there, and we get 12, the same way we got it before, because that's the same expression. So we would find that f of -2 is equal to 12. Now, that tells you something else too, because this -2 was put in place of x. So this is your x value. The value that you got out is your y, right? And we can look up here. When I plugged in -2 for x, I got that y was 12, right? And now I've just pulled y out and I've given it the name f of x. Yeah, I really don't like the notation or the way we say it because both things sound like multiplication because you're always told use of as multiplication in math as well. And it's not multiplication at all. So the last thing you want to be doing is dividing by x to try to get f by itself. That is not what this means at all. This is not multiplication. Okay, so let's go ahead and take a look at another one here. Let's try a little bit farther. There we go. Okay, so let's say we're given, and the name doesn't have to be f. It could actually be g of x, or hell, it could be Bob of x, or Susan of x. I mean, you just make up it's just a name to make up. F is the most common thing because function starts with f. But let's say g of x is equal to negative x squared minus 5x plus 3, right? Let's see what that is. Now, what we want to do with this is just, now keep in mind, the values that I'm plugging in for x right now, I'm making those up. Those aren't coming from anywhere in particular. I'm just picking numbers to plug in. So what I want you to see if you can do is just figure out these things. Let's see if you can find g of negative 2 and g of 0. Okay, so go ahead and pause it here and see what you can get for both of these things, and then we'll go ahead and work it out together here in a minute. Okay, so go ahead and pause here. Okay, so let's go ahead and take a look. Now, this is actually one of the reasons that this notation is nice, because I don't have to keep rewriting this expression. I can just say g now, and you know what the expression is. It's going to be the negative of whatever x squared is, minus 5 times that x value, plus 3. And what I want to do is just take this value and put it in for x. So I put my negative 2 here, and I start computing. Okay, so here's a tripping up point, and I did this on purpose because the negatives always get people here. This negative does not multiply times this negative 2. That's a multiplication which comes after you do your exponents, right? The instinct is to cancel those negatives out, but that is not what's happening. You square negative 2 first, right, which makes it positive 4, and then you apply the negative. So this comes out to negative 4. And then negative 5 times negative 2 is going to be positive 10, so that's a plus 10. And then we have plus 3. And if I go ahead and simplify that, I find that g of negative 2 is equal to 9. Now, I didn't mention this on the last one. I meant to. But again, that means that my x value is negative 2 and my y value is 9, which means that this is associated with a point, the point negative 2, 9, right? Which means it can be graphed. And that's actually where we're going to be going next, is how to get a hold of graphs of these things, just by plugging in some values and seeing where the points fall. Okay, now g of 0. It's the exact same thing. Let's do it in the right color. I'm going to have minus whatever x is squared, minus 5 times whatever x is, plus 3. And so in this case, this is telling me that x is 0, so I'm plugging a 0 into both of these places. And again, zeros are wonderful beings because they kill people. So that dies, and all I'm left with is 3. And so this is associated with the point 0, 3. And the other thing that's important about this is that the x-coordinate is 0. So when you plug 0 into a function, that's actually fairly important because when the x-coordinate is 0, what you're looking at is a y-intercept. So this point right here is actually the y-intercept of this function, right? That's where it crosses the y-axis. Anytime you plug 0 in for x, you are finding a y-axis, or a y-intercept, excuse me. Remember we did that with when we were graphing lines. If you wanted the y-intercept, you plug 0 in for x. If you wanted the x-intercept, you plug 0 in for y. So we did just find a y-intercept of this function. Now, so let's talk about a few more things here. Now, what this is actually leading us into is being able to graph. Excuse me. So let's actually just pick a function and graph it and see what happens. Now, at these early levels of graphing these things, especially when you haven't had much experience with it, your text is kind enough to give you X values to plug in. But later on down the road, as we started investigating these things a lot more intricately, we're going to be able to figure out what X values are good ones to plug in the first place so that we don't have to rely on someone else to give us X values to plug in. But for now, so let's go ahead and take a look at this. Let's say I have f of x is equal to negative x squared plus 3. Okay, so we're going to be looking at this function. Okay, so we can do the exact same thing that we've done in the past. We make a t-table. Generally, and you'll notice this in the homework, it's not an xy table, it's x and f of x. And you notice if I was to write this out with a y, I would be taking out the f of x and putting in y. Okay, so real convenient points to plug in here. -2, -1, 0, 1, and 2. And I want you to see if you can fill these things in. So we'll walk through the first one real quick. And then the last thing I want you to put down is your xy coordinate that comes out of it. Okay, so we'll walk through -2, and then I'm going to turn you loose on the rest of these, and we'll see what happens. So if I want to find out what happens when x is equal to -2, what I'm going to do is look at f of -2. So that's going to be the negative of -2 squared plus 3. Let's see here. -2 squared is +4. So that's going to, and then this negative makes it -4 again. Plus 3 is equal to -1. So that means I get -1 here. And that means that the coordinate that I will be plotting is the point -2, -1. We'll get to the plot here in a few minutes. What I want you to do right now is just go ahead and see if you can fill out the rest of these values in here, right? For -1, 0, 1, and 2. And then we'll come back and fill it in together to make sure we understand where everything came from. And then we're going to graph it because we're just exciting like that. Okay, so go ahead and pause it here, and then we'll take a look at the rest of these values. I'm just going to watch you work. Okay, so let's go ahead and take a look at the rest of these things. So I'm going to get this off of here. But you'll notice as we go through these, it's the same computation each and every time. So let's see here. So we have -1 is next. So at -1, I have f of -1 is equal to the negative of -1 squared plus 3. So that makes it +1. That makes it negative again. So I get 2. So let me get these guys off of here. So I get a 2 here. Okay, that means I have the point -1, 2. And then 0, well, zeros are nice. I mean, we've pointed out before that zeros kill people. Right? So that term is just completely gone, and I get 3. So at 0, I get 3. So I have the point 0, 3 here. Notice again, the x-coordinate is 0, which means that this is a y-intercept. This is where it crosses the y-axis. So that one went really, really fast. Let's try f of 1 now. And so that's negative of 1 squared plus 3. So that's -1 plus 3 is 2. So that means I get a 2 here. So that means I have 1, 2. And for 2, f of 2, let's see, 2 squared is 4. If I throw the negative on there, that makes it negative 4 plus 3 is negative 1. And so I have the point, let's see here, 2, negative 1. Now, those aren't very meaningful until you have it on a graph. So let's go ahead and take a look at what this would look like on a graph here, shall we? Okay, so let's go ahead and plot these points here. So first we have the point negative 2, negative 1. So that's negative 2, negative 1. So that puts it, oh, let's turn the pen back on. Negative 2, negative 1 is my first point. And then I have negative 1, 2, so that's here. Okay. And then let's see, we have 0, 0, 3, so that's here. Well, those are definitely not on a straight line, are they? Everything we've graphed so far has been a straight line. This is not a straight line, you can tell. And then we have the point 1, 2, and then 2, negative 1. And so you notice some things here. One, this is kind of symmetric, right? If I draw a line down the middle here, those points will line up with each other. So this thing is it's symmetric. And let's see here. Now, it turns out, unless you plotted a bunch more points, it'd be hard to tell this, but this is actually a smooth curve that starts here and heads off this way and does the same thing on this side. Right? And so it ends up curving this way. Now, as you go through different examples of this, you're going to see these things curve all different directions. You'll see some that go up like this, right? Some are going to be wider than others. Like you can tell this one's wider than the first one I put down. And they can be upside down. They can go all different directions and do all different sorts of things. We won't see this example, but they could even be sideways, right? They could open sideways. In any case, this is just going to be you kind of plotting through these things and seeing what happens. It actually turns out, like you notice here, the exponent is even, right? Anytime the exponent is even, you end up with this kind of a U shape in one way or another. But let's see, is this gonna, oh, I'm erasing the entire graph. Well, that's okay. It actually turns out that, well, we're gonna try this. I'm gonna see if I can connect this line. There. That's actually not too bad. But it actually turns out that if that exponent is odd, if your polynomial is of odd degree, what happens is this thing goes up one direction, but it goes down the other. And sometimes it could go this way instead. Right? So it ends up with this little twist. It could. And so do be aware of that too. So you're going to get different shapes as you go through this. What this is a chance for you to explore a little bit. Now, one of the things that you are going to be asked about these shapes is what their domain and range is. Okay, now that's something, there are ways of getting a hold of that. But, yeah, there we go, I'll write it here. It's a lot easier if you just look at your graph to be able to see what the domain and the range is. What the domain is the set of all inputs to a function. Okay, now normally this is explained by telling you that this is the x values, and it is. I'm going to put that in parentheses. But I always feel a little nervous saying that because they're not always the x values. The domain are the input values, and you could honestly be using any variable for an input to a function. If you're talking about how things change over time, then your domain variable is t, right? Because t is what's usually used for time. So it doesn't have to be an x. What it is an input. So as long as it's an input, it's part of the domain. The range is the set of all possible outputs. Right? It's all the things that the function spits out. And if you think about it, what do we do with functions? At least up until this point, what we've been doing is sticking in x values and getting out y values. And so the range is the set of all the possible y values. Again, it could be a different variable, but for this context, it's fine to think of it as all y values. Excuse me. Now, when we look at a function, in fact, let's look at the one that we just graphed. It was f of x is equal to negative x squared plus 3, right? And we noticed some things about this. I'm just going to scratch out a graph here. It had a y-intercept at 3, right? And it did this, more or less. I'm just going with a sketch. It turns out that y-intercept, it's not always the y-intercept, but you notice this is the high point of the function. That's where it turns around and starts going back down. That's the point that's going to be important when we start talking about the domain and the range and stuff. Okay, so for the domain here, the domain, well, let's just think about this. If we look at this function, are there any x values that are going to cause problems? Now, basically what it means to cause problems is you have trouble getting a y value back out of it. So are there any numbers that you can't square, make negative, and then add 3 to it, right? You want to think, are those operations legal on every number? And they are. It doesn't matter what number you pick, you can do all those things to it. So there's two ways to designate the domain here. And it will change just depending on what book you're using, what level you're working at, and what you need to use it for. Right now, it's all real numbers because you can plug everything into it. So you may see it written this way, which I believe is how your book is doing it, which is a double stamped R, right? And that represents all the real numbers. The other way to write it is in interval notation, and all real numbers as an interval would run from negative infinity to positive infinity and everything in between, right? Now, the range. Okay, so the range are all the y values that you can get out from plugging in x values. So if we look at this, this is where it's a lot easier just to look at your graph. Well, this thing tops out at 3, right? That's the highest y value that I can reach with this function. There's no function values that will give me a 4, a 5, or anything else. Now, if I go down, any line I draw, I can always just extend this function until it hits it, right? So I'm going to be hitting y values all the way down there, which means that the y values start at negative infinity and travel all the way up to 3. And 3 is an included value, so we put a square bracket on 3. I know you probably thought that notation was not going to come in handy again, but it is. Because all the y values you reach are when y is less than or equal to 3. And you notice that's the graph for y is less than or equal to 3. Okay, so it's really a matter of looking at it. If you have something, in fact, let me go ahead and clear this off here so we can look at some more examples. If you ended up with a function that looks like this, oh, not like that. right? If it ends up being one of these twisted ones that does this. Well, you'll notice for the domain, um, and you can tell from the function, but it turns out the domain of this is all real numbers, because no matter what x I pick, I can go up high enough and find a y value that goes with it. And so all x values are legal to plug in. The range, right? We want to ask ourselves, what are the y values we're getting out? And so if I look at this, I have y values. No matter how far down I go, there's a y value. This goes on forever in both directions. And so it turns out the range in this case is all real numbers, right? You can have other cases too, like this one isn't technically a function, but let's say I have a circle, right? It still has a domain and range. Yeah, let's say we have, so let's say that's at 1, and this one is at 5. So this would, let's say this is the tops out at 4, and this one bottoms out at 2, right? Whatever this shape is. So for something like this, your domain is not all real numbers now. It's all the x values that you can plug in, which run from right here to right here. So it only runs from 1 to 5. Those are my only legal x values. But they're both included. So it's a closed interval from 1 to 5. The range runs, oh, that's -2. Runs from down here at -2 all the way up to 4. And so that means that my range goes from -2 to 4. I know this isn't drawn well. This is actually an ellipse, the way I've picked the numbers. But this would be the idea. It's basically, what can you contain the function in? And in this case, it's this box here. And what you're really just doing is describing the dimensions of the box, right? We're going to be more focused on these things, right? The polynomial functions. But just know that domain and range applies to everything, every function, not just polynomial functions. There are a lot of types of functions out there. Okay, so let's go ahead and clear this off. Okay, so let's test ourselves here. Let's see what we can do. So I'm going to give you a function. I want you to graph it and find its domain and range. So let's say we have h of x. Again, it's just a name. F, G, and H are the common function names, so I'm just trying to use them all so you get used to seeing them. Let's say it is x squared. Well, let's just do it this way. -4. Let's just do it from there. And then the x values I'm going to give you. Oh, not f of x. Are the same ones that you had this last time. Okay. And so go ahead and pause it here and see if you can graph this guy. And then we'll take a look at it together. All right, so let's go ahead and take a look here. So I've got the pen on, and let's see here. Actually, let's make this a little bit bigger. There we go. That's better. Now, if I plug in -2 and square it, right, that gives me 4. 4 minus 4 is 0. If I plug in -1 and square it, right, that gives me 1 minus 4 is -3. If I plug in 0, well, 0 kills everybody, right? So I'm left with -4. That's it. And if I plug in 1, 1 squared is 1, minus 4 is -3. And then if I plug in 2, I end up with 4 minus 4, which is 0 again. Now it's interesting. Here, these are y values. I have a y value of 0. which means if the y value is 0, that means you have an x-intercept, right? If the x value is 0, you have a y-intercept. The y value is 0, you have an x-intercept. So we've actually found both here. So let's go ahead and graph these. Let's look at what points we have, right? Here's our xy. And that should be -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. And you notice it's symmetric, right? That's one of the properties of these types of these particular types of equations. Some of them are symmetric, some of them aren't. But it turns out if they have an even exponent, they're usually symmetric. So let's plot these things. So -2, 0 is right here. Yep, that's an x-intercept. -1, -3 would be down here. 0, -4 is here. 1, -3 is here, and then 2, 0 is here. Right? So again, there's this line down the middle, and I can see that both halves are the same. And so this will go up this way and continue. It does go on forever. Technically, if you just stop it right there, that's incorrect. Because you're telling the person who's reading it that that's as far as the function goes and it doesn't continue. So you do have to put these arrows on there to make sure it's clear that the function continues in the manner that you can see. Okay, so we have that much. So now we need domain and range. Now it turns out for all polynomial functions, and this is actually just a general property of polynomials, their domain is always all real numbers. Right? Those are always all real numbers. If it's a polynomial, you can plug anything you want into it. The range is what's going to be a little dicier. So we need to take a look at this. The range, let's see, the lowest y value that I have is down here at -4. I don't have anything below that. So that means that the lowest value is -4. And then if I start moving this way up the y-axis, I can see, because these arrows tell me that this continues, I'm going to be hitting any y value that I want. I can always achieve any y value. And so that gives me an infinity. -4 is actually a point on this curve. So that it has a square bracket, and infinities always get round brackets. And so it's a little bit different. You have to do it geometrically right now with the domain and the range. You just have to get it plotted and then take a good look at it and figure out what you're looking at. All right? Okay, so those are the main things we needed to hit for this lecture. And so until next time, keep your pencils and your wits sharp.